Yes.
We'll see. Maybe depending on the size of the session, maybe people can unmute at the end, but just see how many people are here. And then Etienne, oh, it looks like you just made Yang a co-host, so that means
The last one, I don't remember the name. Maybe I don't.
Zojun,
Yeah,
you.
I'm Jude.
Am I
June,
saying
you
your
are the
name
last
right?
speaker of the session? Okay, so you're also covered. And it seems that now we are on YouTube.
Okay. Do you Yang and do you want to test your slides real quick?
Okay, yeah.
Just make sure you can screen share and everything.
So we'll
All right.
read it.
And get animation. Okay.
Yep, looks good. And then so June.
Can you see my slides?
Yes.
Yes, I
Oh,
can.
okay.
Great. Yeah. So yeah, I guess to the speakers, yeah, you have 30 minutes total, but that includes questions and transitions. So yeah, hopefully you plan for like a 25-minute talk.
Yes.
Does anybody want like a minute warning or anything like that? Or do you not want me to break in and remind you how much time you have left?
It might be helpful to have like a warning when we absolutely have to be off, like a minute before, 2 minutes before, or something like that.
Okay.
I don't think my presentation will, hopefully I'll have some time for questions, but you know, on the odd chance that I screw up my timing.
Sounds good. Yeah. Okay. Yeah, I'll just maybe give a 2-minute warning or something like that.
Sure.
Etienne, were there a lot of people at the talk this morning? I was kind of just getting up and getting ready, so. Or not this morning, I guess, this afternoon.
During Olivier talks, I think we were on the Zoom meeting around 40, 45.
Okay.
If it's as yesterday, half goes on each channel. There are also a lot of people on YouTube. We don't know if it's the same.
Right.
So
Yeah.
yeah, the best is you wait. Yes, I think Olivia stopped his talk 30 seconds now. So
Yeah, so people
Right.
start filing in, yeah. And there's nothing to do with the YouTube people, right? I only
no,
need to worry about Zoom people.
I just have a look if someone I think that people on YouTube cannot
Ask questions or talk, right?
They have only access to the chat. So if there is a question on the chat on YouTube, I write again the question on Zoom and you can see it on the Zoom chat.
Okay. Sounds good. All right, so I guess we'll start in 2 to 3 minutes. Looks like folks are starting to file in from the previous talk.
Okay, I turn my microphone off now, Zach, and you're the boss of the session.
Okay,
Chair.
sounds good. Thanks, Etienne.
I'll go ahead and share my slides here.
Sounds good. Yeah, and we'll be perfectly on time. So all right. Yeah, we're about a minute out. And then we can start. Okay. Great. So, yeah, I guess it's almost 1600 Berlin time. So I'll go ahead and welcome everybody to our session this morning on phase amplitude reduction. It's focused on new methods in phase amplitude reduction, augmented phase reduction, isostable isochrone coordination, and really recent results on more accurate analysis and more efficient simulation over broad ranges of limit cycles and results of perturbations to them. So we have a great collection of 4 speakers this morning. Dan Wilson is our first speaker from University of Tennessee, and I'll let him take it away. Just before that, if you have questions during the talk, you can go ahead and drop them in the chat. At the end of the speaker's talk, I think we're a cozy enough group that you can unmute and ask questions if you like, or just send them in the chat. So go ahead, Dan. Thanks.
Thanks, Zach, for the introduction and also for the invitation to speak today. As the title suggests, I'm going to be talking about model order reduction strategies for oscillatory dynamical systems. And the main result that I'm going to be talking about today is this adaptive reduction paradigm, which can allow for the implementation of larger inputs in reduced order models without sacrificing accuracy like you usually do for standard phase reduction strategies. I'm going to talk about a couple applications where this is useful and then give some concluding remarks. So the motivation, we're thinking about studying oscillatory dynamical systems in reduced order coordinate framework. And there's lots of applications in biology where oscillations can emerge. So for instance, this is a neuroscience conference, so we see oscillations in neurological rhythms. We also see oscillations in circadian cycles, where there's a 24-hour or approximately 24-hour period of oscillation so that you can entrain to a 24-hour light dark cycle. You have heart rhythms or arrhythmias, which can have oscillatory behaviors. So just in your mind, you can think about maybe a tonically firing neuron. So this is computational simulation data from a compartment-based tonically firing neuron. There are inner spike intervals, which are approximately the same from spike to spike, although there's some noise in the system. So it's not exactly the same, but these are the sorts of systems that we'd like to be able to understand in a reduced order coordinate framework without necessarily having to deal with state variables like ionic concentrations or gating variables or all sorts of other things. So to start out, there's a lot of different strategies that have been developed over the years for reduced order modeling of oscillations. I think one of the most elegant is that if you can find an invariant submanifold or an aggregate order parameter, so think like, for instance, the Kuramoto model and the Kuramoto order parameter, although there's been a lot of more recent instances of this, you can take a big population of oscillators and represent them with a couple ordinary differential equations. The trouble is that it's really difficult to find invariant submanifolds, so oftentimes you have to use other methods. Phase reduction is a really popular one in the neuroscience community, which was really developed by Winfrey in the 60s and also Ermentrout and Capel later on. More recently, Koopman-based methods have become popular, and Koopman operator theory says that you can represent any nonlinear dynamical system in terms of a linear but possibly infinite dimensional operator. And also phase amplitude based methods have gained traction in recent years, where you take the phase coordinate and augment with an amplitude variable to get some of the information about the dynamics that are transverse to the periodic orbit. The strategy that I'm going to be talking about today is kind of a combination of these bottom 3 things. So just first, a little bit of background about model order reduction of oscillators. If you have an oscillatory dynamical system and you're interested in the timing of those oscillations, you can work in phase coordinates, which essentially say, or they encode for the timing of those oscillations. So you can define a phase, which ranges between 0 and 2 pi on a limit cycle, and you can scale it so that the time derivative of the phase is equal to a constant on that limit cycle. And then you can say, well, if I want to extend phase to the base of attractional limit cycle, I can use the notion of isochrons, which essentially say that if you start on the same isochron, you're going to end up in the same spot in the limit as time goes to infinity. So in this slide, I'm showing a two-dimensional representation of Hodgkin-Huxley equations. We have voltage on the x-axis and a gating variable on the y-axis. This system has a stable periodic orbit, which I'm showing in gray here. And I'm plotting out all the isochrons for the system in various colors. And not surprisingly, if you take two initial conditions, one here and one here, on the same isochron, if you integrate the behavior forward in time, they both approach the periodic orbit, and they do so together. They end up in the same spot in the limit as time goes to infinity. Now, using this notion of phase, you can end up with a good reduction in the dimensionality using something called a phase reduction. So by restricting your attention to a very close proximity of that limit cycle, you can end up with dynamics for the phase variable that follow d theta dt is equal to that constant omega, the natural frequency, plus z of theta, which is the gradient of the phase evaluated on the periodic orbit, multiplied by an external input. So this is useful because it allows you to go from an n-dimensional system, where n could potentially be large, to a one-dimensional system where you're just thinking about the phase of oscillation close to that limit cycle. The problem with this is that you really only get a good picture of what's going on near the periodic orbit. If you have an input that kicks you into this region or this region here, standard phase reduction methods aren't going to be able to tell you what's going on, because you're going beyond that limit where the local linearization is a good approximation for the system dynamics. And so the big questions here, and a couple that I hope to give a decent answer in this talk, is how can we handle larger magnitude inputs? So for instance, to give us information about what's going on in here and what's going on here at the edges. And how can we do that without adding too many extra dimensions? And then also, what does this allow us to do that we couldn't do, say, simply using phase reduction methods that are working in the weakly perturbed paradigm? So this brings me to the main result that I want to talk about, which is this adaptive reduction paradigm, which is kind of an extension to standard phase reduction. So the main idea I'm going to describe on these next couple slides here. For the moment, we can think about, for concreteness, a three-dimensional model that's of gene regulation that's sometimes used to model circadian oscillations. So we have three variables, B, C, and D. Those describe the dynamics. And we have this term LC here, which you can think about it as a constant value of light input. So when the light input is 0 for this model, we get a stable limit cycle that emerges. It's showing here over in blue. And it's about 24 hours. If you take a look at a trace of the variable B for this periodic orbit, it's about 24 hours. That's a stable limit cycle. But for non-zero constant values of this light, we also have other periodic orbits that emerge in steady state. So a continuous family of periodic orbits, as I'm showing here, as these black lines adjacent to this nominal blue periodic orbit. And as I mentioned previously, phase reduction starts to have problems if you push yourself out too far from a nominal limit cycle. So the idea here is maybe we could use this collection of periodic orbits to kind of adaptively update some nominal periodic orbits, so we'll stay at least close to one of those nominal limit cycles. The main idea behind that, as I'm showing on this slide, suppose you have, in this case, two discrete periodic orbits, one blue and one red, each which emerge for a different collection of nominal constant values of some parameter. If we have some initial condition that's close to, say, this blue one, initially we're going to have a good representation if we try to do some sort of phase reduction. But as we start to get further and further from the blue one, that representation is going to get worse and worse. And you might say, well, maybe now I'm just closer to this red periodic orbit, and I want to convert my coordinates in reference to this red one so that I'm close to this next one as well. So this is kind of a cartoon schematic of that general idea implemented with a discrete number of periodic orbits. But the idea of what I'm going to talk about is the same. We want to handle the reduction of dimensionality in terms of a continuous collection of periodic orbits so that we're never too far from any one of those individual orbits. So that's what I'm going to talk about in this mathematical approach, in this derivation, in the next couple of slides. We're going to assume that we have some nominal system. The state is X, F gives the dynamics. P0 is a nominal collection of parameters which is potentially constant. It doesn't have to be changing, although it could be. And then U of T is some external input. So from a neuroscientific application, think this might be an external, DBS probe or something like that, that has the potential to change, influence the voltage behaviors and influence the spiking rates. So this is the actual system with the actual dynamics, and we're going to represent this in terms of a shadow system. So we're going to take this and think about it in a slightly different way. Instead of x dot is equal to x comma p0 as the nominal dynamics, we're going to have x dot is equal to f of x comma p as the nominal dynamics. So this is not necessarily the actual nominal parameter set, but it's going to allow us to represent the behavior in terms of some different limit cycles, as we saw in the previous slides. And then to that, we're going to add this effective input, which is just everything else so that this shadow system and the actual system dynamics are exactly the same. It's just in this case, UE is this effective input, which is different from the nominal input that's being applied at a given moment. So just some assumptions before we continue this derivation. We're going to assume that we have some continuous set of allowable parameters P. We're going to assume that each of them gives a stable periodic orbit, which is potentially different from all the other orbits. We're going to assume that for a constant value of P, we can represent the dynamics in a basis of reduced order phase amplitude coordinates. So here we're going to be using isostable coordinates, which represent level sets of the slowest decaying components of the Koopman operator, but you can use other amplitude coordinates if you want. So, and this is a well-established strategy. It's just saying if we have a constant value of P, we can represent the dynamics near a given periodic orbit. We're going to also assume that the periodic orbits are continuously differentiable with respect to theta and our parameter P, and also that these reduced order coordinates theta and psi j are continuously differentiable with respect to x and P. So with that out of the way, we can change variables like we do in standard phase reduction to go from our state coordinates to our reduced order phase and amplitude coordinates. These depend on two variables now, so we get two things emerging out of this chain rule here. And the first of these components are easy to get. These are in fact what we get anyway from a standard phase amplitude reduction if we just have a constant value of P. This is that assumption I made earlier that says we can represent the behavior close to some nominal periodic orbit in terms of this phase amplitude reduction. You can see this looks similar to the standard phase reduction. We have some nominal value of the natural frequency. Here's a phase response curve multiplied by this effective input. And then we have some higher order terms here that give slightly more accurate corrections. The question becomes, how do we get these terms? And these are the ones that are going to tell us how do our phase and our amplitude coordinates change if we change the nominal parameter set, which effectively changes the nominal periodic orbit we're analyzing everything in reference to. So we have to figure out how these are going to change in time. And it turns out we can do this relatively straightforwardly, just taking some partial derivatives. So we take a look at the phase coordinate near the periodic orbit first. We do an asymptotic expansion up to second order accuracy. We have some nominal phase here. Here's the gradient of the phase, which is also the phase response curve, multiplied by the deviation between the state and the nominal periodic orbit itself. We have some second order terms. Here's the Hessian, and then we truncate finally after third order. We can take a partial derivative with respect to the individual parameters of this equation. Again, this is straightforward, recognizing that if you take the partial of the state itself with respect to a parameter, you're not actually changing the state of the system. Again, this is the shadow system that we're using to represent the state dynamics. You're not actually changing the state when you're changing the nominal parameter set. So if I take the partial of the state x with respect to pi, I'm going to get 0. If I take the partial of the underlying periodic orbit with respect to pi, that's going to be non-zero here. And everything else follows like you would expect when you take partial derivatives. We can do some simplifications to represent that result in terms of functions that we already know, some first order, some second order terms. And at the end of the day, we can combine and get equations that look like the partial of theta with respect to our parameters are equal to some function d of theta comma p. This is evaluated on the limit cycle. And then we have some higher order corrections, this linear combination of functions ek multiplied by our amplitude coordinates. And we can do a similar thing for all of the amplitude coordinates as well to get the partial of them with respect to the collection of parameters. And finally, we end up with this big mess of an equation, which is this adaptive phase amplitude reduction. Now, it looks like, there's a lot of terms here, but essentially, we're trying to figure out how the phase evolves in time, how the amplitude coordinates evolve in time. And we have the ability to change these nominal values of our parameters. And we can do this however we want, with the goal being that we want to keep the actual state close to the state on one of the limit cycles that we have available. And to do this, we have P dot showing up here and P dot showing up here. We can use this to try to keep, design GP appropriately to try to keep the amplitude coordinates small, so that if those coordinates are small, we're always close to one of the underlying periodic orbits, and we get a nice reduction that adequately reflects the dynamics. And then, of course, we can represent the actual state of the system in closed form in terms of the reduced order variables here. So a couple things to keep in mind. Again, that's a lot of equations, but the big takeaways from this strategy is that provided we can come up with a GP, again, this update rule for the adaptive parameters, as long as we can come up with something that allows us to keep all of those isostable coordinates, those amplitude coordinates small, in this case, order square root of epsilon, then we can give whatever input that we want and still get an accurate representation of the reduced order equations, accurate to order epsilon. This is in direct contrast with most standard phase reduction strategies, which generally require either the magnitude of the input to be small or the input to be varying slowly or something like that, which are generally restrictive conditions. In this case, we can use whatever magnitude input that we want and still get an accurate reduction. So this is going to allow us to approach problems that would otherwise be intractable. So here's a couple applications where this ends up being useful. We're going to think about the same circadian model. In this case, we're going to have a bunch of oscillators, 10 in this case, each with 4 separate variables, and they're coupled through this mean field value of D in through here. We also have this adaptive parameter. Again, think about this as a constant light input. And then we have this L of T term, which can be used to implement a light dark cycle or just any light input that you want to see how it changes the behavior. Using this adaptive reduction strategy, we can go from 40 states, 4 times 10 is 40 states, down to 5 states. So that's 1 phase, 3 amplitude coordinates, and 1 adaptive coordinate. And we end up with very nice results and better, in fact, than a lot of other standard phase-based reduction methods in terms of representing these dynamics. So here we have this black line is what if we do standard phase reduction on this. Red is the second order version, which is accurate to a little bit more accuracy. Extended phase reduction is has the explicit assumption that the input is changing slow enough to get a good reduction, and then this adaptive phase amplitude reduction. The blue one is the only one that works in this case. All of the other ones have this drift over time, and they really don't give a good representation of the overall dynamics. And of course, this gray line is the full model. You see the gray and the blue match pretty well. All the others, it's your best guess as to what's going to happen. So we have a model that does a good job of representing the dynamics of a high order model in a reduced order coordinate system. Now we can think about applying some of these strategies for control purposes and then use the resulting answers to see how well it works on the overall model. So in the second application, we're going to consider the same system In this case, it's going to have 3,000 oscillators, so a lot more. There's going to be some heterogeneity, and there's going to be a little bit of noise in the system. But we can still do this adaptive phase amplitude reduction to get a reduced order model. We're going to come up with a control problem. In this case, if you're using a model that's based on circadian oscillations, you might think about, well, can I come up with a light avoidance or light seeking strategy to mitigate the effects of jet lag? So that's the problem that we're thinking about here. So we have some nominal value for an entraining stimulus, like a 24-hour light dark cycle that you all are entrained to in your home locations, so that you can maintain an appropriate sleep-wake cycle. We have this adaptive parameter L0 here, which is going to be used in this adaptive reduction, and delta L of T is going to be used to implement this light seeking or light avoidance strategy. And the rules of this optimal control formulation are going to be such that we start from a fully entrained solution. Then we're going to consider all possible stimuli that shift the phase appropriately in response to a change in the rapid travel across multiple time zones, for instance, to simulate jet lag, and try to find the one that minimizes the L2 norm of the effective energy. So this delta L squared, find the one that minimizes the control effort. We can solve this by applying a calculus of variations framework, finding what are the Lagrange multipliers, find the initial values of those Lagrange multipliers, and solve for the optimal inputs. We do that, and we get these results here. So in this figure, I'm showing the recovery time when we apply a couple different strategies to try to find a good delta L of T, a light seeking or light avoidance strategy. This black line here is basically if you do nothing. If you shift your time zone, you shift your 24-hour light and dark cycle, and see how long it takes you to recover to that new, the new time-shifted 24-hour light and dark cycle. This red line here is using a phase amplitude reduction strategy. We use this in the control formulation. It's essentially phase reduction valid to first order accuracy. And as you can see here, nominally, if you don't do anything, sometimes you'll get a better result if you implement this strategy that's suggested that comes out of the optimal control formulation when you apply it to the real model, but sometimes you get a worse result here. It takes longer to recover. When we apply this adaptive reduction strategy to get those inputs out of that, we're able to relatively quickly re-entrain to this new target, fully entrained light dark cycle. So similarly in panels B and C here, we show those actual inputs that are predicted or that come out of using this optimal control strategy. We have two big pulses here for this one that doesn't work, two slightly smaller pulses for this adaptive reduction strategy, which does work for the plus 7 hour time advance. For the minus 10 hour time advance, we have different inputs. And we can see that when we apply this to our system, looking at model observables, here with this dashed line is this fully entrained reference. These initial conditions are minus 7 hours too slow, so we have to advance them by plus 7 hours. Applying this input allows you to get relatively quickly, when using the adaptive reduction framework, to the fully entrained solution that you want. The other ones don't work quite as well. And it's basically the same story for the minus 10 hour time delay as well. One interesting thing to fall out of this is, in something that's not mandated by the optimal control formulation at all, is that if you want to shift the phase of a large population of oscillators quickly, it seems to help to desynchronize them first. And we can see this in a number of different ways. And so this is for the application I showed previously. We're trying to respond to a time advance of plus 10 hours, so we have to shift the phase by that amount comparably. If we see traces of these model observables, time is equal to 0, we start our input, we have this big first pulse, and it really desynchronizes the phases of these oscillators. And in fact, it kind of destroys a lot of the oscillations initially, only to resynchronize to the new and correct time zone that we want. We can see this also in the raster plots and the effective locations, that the phase is equal to 0, a big desynchronization first, followed by a resynchronization. We can also see this looking at the Kuromoto order parameter in a rotating reference frame. Initially, we're all synchronized in our old time zone. We apply this input and we kind of go slowly through the middle of this rotating reference frame, which indicates desynchronization, to emerge at the correct re-entrained phase. This is for a plus hour time advance. Likewise, we have the same story for a minus 8 hour time delay. So initially we have this input which desynchronizes, and then we resynchronize to the new correct time zone, going through the middle here and re-emerging at the correct location with respect to the 24-hour light and dark cycle. So again, this isn't something that was mandated by the control strategy. This is just something that emerges for large shifts for a population of oscillators. And it might be something to look into further that perhaps might be universal. So some conclusions are these standard phase reduction techniques. They work really well when you're considering small magnitude inputs, when you stay very close to the underlying limit cycle. But they tend to fail if you apply large magnitude inputs, or if you're in a situation where you need a large magnitude input. This adaptive reduction strategy, where we're having some nominal, some adaptive parameter to try to keep you close to some underlying limit cycle, can be used to add maybe a couple extra states to your reduced order model without having to sacrifice accuracy if you're using very large magnitude inputs. And the resulting equations, as we've seen in the couple examples I've shown, remain analytically and numerically tractable in many applications. So just really briefly, some future and ongoing work. In most of the applications I showed today, in order to implement these adaptive reduction strategies, you need the model equations. In real life, usually you just have data. So it's important to be able to infer these types of reduced order equations from observable data in the case where you don't have the equations available. And there are some various approaches. One that looks promising is this machine learning based approach, essentially to get the right coefficients on the reduced order model. So that's something that's going on as we speak. Adaptive reduction strategies for arbitrary trajectories. One thing about these results is that it requires a stable periodic orbit, and you can't go through bifurcations. We assumed that there was a certain level of continuity, and if you go through a bifurcation, that continuity goes out the window. So being able to extend this to arbitrary trajectories would be useful if you need to consider situations like a transition through a Hopf bifurcation from an oscillating solution to a stable fixed point, and vice versa. And of course, there are a lot of applications where this is useful: circadian, cardiological, neurological applications to high-speed flows where you see oscillations, where these reduced order strategies are useful. Here's some references to some of the things that I've talked about today. And I'd be happy to answer any questions that you have at this point. Thank you.
All right. Feel free to applaud with the reaction. I have a question from Peter Thomas. Is there any evidence that the quantitative desynchronization of the oscillator during recovery from a large time shift is related to the qualitative feelings of discomfort experienced during jet lag in real life?
Yeah, I mean, that's a really excellent question. You know, in a lot of the literature for people who actually work, you know, on real life humans instead of models, the idea is always that there's some mismatch between the phase of the oscillation and the phase in your new time that's causing jet lag. But I think that it's likely that an unaccounted for factor is that there's some sort of mixing up of the you know, you have all sorts of bodily organs that are responding to inputs from the suprachiasmatic nucleus, and you're probably mixing up some of the relationships between the phase of oscillation between those individual things, which would be like an amplitude coordinate shift. And that's probably also causing some discomfort as well. And so, yeah, I think that's a great question that would probably, you know, require somebody who knows what they're talking about for you know, actual you know, the physiology and how people feel. But yeah, I think that's an unaccounted for thing as it currently stands.
Great. Thanks, Dan. Oh, looks like we got a couple more. So I'll go with Rachel's, and then Tony, you can unmute after this one, I guess. Rachel Nix asks, is there a general strategy for specifying G sub P to update P in the adaptive framework?
Yeah, that's a good question too. So if you have a low order system, so if you have one amplitude coordinate, one thing that you can do is set this GP here, which essentially sets P dot here, such that it kind of mimics this term in here. So multiply it by this term itself, and then times the isostable coordinate and times a negative constant. And so suddenly this acts like an exponential decay that's time varying. So you multiply it by this term, so you get a positive number, and then multiply by a negative constant. You kind of shift the exponential decay to larger values. That's one thing that works. You can also solve such that you cancel out this term here with the update rule. That only works under certain circumstances. But the short story is if you have a couple coordinates, there are good ways to do it. If you have multiple coordinates, it's sort of, I don't have a good systematic answer for how to do that. You sort of have to do it on an application by application basis.
Thanks. And then Tony had a question.
Yeah, I prefer to do that just
Go for it.
speaking, because it's not easy to write down this. Hi, Dan. Nice
Hey,
talk.
Tony, yeah,
Thank you.
Good to see you.
So I wanted to ask just the feeling, I mean, this adaptive method seems that improves some of the advantages of the extended method with phase and amplitude. And is that, I mean, the key point is this variable P that you introduced here. And also, I didn't understand, I think, the philosophy. You want to stay close to some P0 all the time, or you allow to the G to travel along across the P's?
So thanks for the clarifying question. So the idea is, here's your nominal periodic orbit. You've got all of these other orbits that may exist in the state space. And suppose you shift, you give an input that shifts you in this direction. Now you're kind of in this region over here. You're far from this orbit, but maybe you're close to this orbit down here. So if you can sort of represent your system in terms of the dynamics around this orbit, and lump everything else and call that a perturbation, then you can get a good reduction that's close to your nominal orbit, so that you're not too far away from the nominal one that you're thinking about. So it allows you to kind of, in an intelligent way, update your effective limit cycle so that you stay, and hopefully to be able to stay close to at least one of these orbits here.
Okay, thank you. Yeah, so it's like you are just trying to monitor which is the limit cycle you are following at
and not explicitly monitor, rather monitor in the sense that we keep the amplitude coordinates small. That's exactly right.
Yeah, I see. Thank you.
Right. And then one real quick question from Mustafa S.
Yes, thank you. Hi, Dan. So you compare your approach, the first order approach, second order approach, and the final this approach. And in some case, the second order approach gives, worse results than the first order. So I think the idea of increasing order is the increasing the accuracy. So why the second order gives worse?
Well, yeah, and that's a good question too. I mean, for both first and second order are based on asymptotic expansions about the periodic orbit. And once you go beyond those asymptotic expansions, all bets are off. And so the magnitude of the input is so large that it doesn't work for first order, it doesn't work for second order. And at that point, maybe you'll have something that's good and maybe you won't. But it's just illustrating that, maybe if you took it out to third, fourth, fifth, whatever order of expansion, maybe you'd be able to get something, although that even has its own limitations as well. But in this case, second order just doesn't work. Neither does first order.
Okay.
All right. Well, thanks again, Dan, and thanks for all the great questions. We'll turn it into Yang Wang now from University of Iowa, and take it away, Yang.
Thank you for the invitation and for the introduction. So I'm gonna talk about shape and timing perspective of using this variational analysis to dissect motor robustness. I'm gonna start with some key questions in motor control. One of the remarkable feature of mode controls that behavior are both robust and flexible. And by that, I mean by the robustness, I mean the ability of the system to maintain its performance despite perturbations, and flexibility is that the system is able to deploy alternative strategies to improve fitness. So it's important to understand this robustness and flexibility and also the roles of sensory feedback and biomechanics. In today's talk, I'll focus on understanding robustness and try to understand what roles the sensory feedback and biomechanics are playing here. So to do that, to dissect motor robustness, we need models for given biomechanics control systems. And then with the model, we can define task fitness, or what we can call that performance. Once we have that, we can apply perturbations. And here the perturbations I'm considering is small. We apply perturbations that's gonna potentially change in both timing and shape of the limit cycle system, which will then together influence the performance. Then we ask how much the performance changes due to this perturbation. So because both shape and timing of the limit cycle have changed under the parametric perturbation, so we need tools to track both changes. And then with the tools, we can determine what factors contribute to robustness and how they contribute. So this is the approach that we are going to use. And the kind of system I'm going to consider is the feeding behaviors of the sea slug Aplysia. Okay, so Aplysia is a type of sea slug, and it feeds on seaweed using an organ located in its head called the buccal mass to pull the seaweed into the mouth during the feeding. And here the movie showing here is showing that an Aplysia swallowing a seaweed, and also a cartoon here. And the perturbation that we apply here is on this seaweed when the animal is swallowing the food, a small mechanical perturbation. The ingested behaviors of this system can be decomposed into 3 phases. One is the protraction open phase. That is saying the animal, the grasper, is opening and protracting to reach the food. And then it closed on the food while still doing retraction. So that's protraction closed phase. Then it pulls the food back to the mouth. That's the retraction while it's closed on the food. So during the retraction closing phase, the animal is swallowing the food. So this is the system we're going to consider. And here is the a cartoon showing the 3 different phases. Corresponding to them, there are 3 neuron pools. A0, A1, A2 represents the firing rate of these 3 neuron population, and they are mutually inhibiting. So this term represents the sensory feedback depending on XR, which is the grasp position. This neuron population, activation of this neuron population will activate some muscle activation. For example, A0 and A1, corresponding to protraction open and protraction closed, will activate U0, that's the protractor muscle activation. And A2, that's the retraction closed related to neuron population, will then activate U1, that's the retractor muscle activation. So these 2 muscle activation together will generate a force that we denote as F sub muscle. This force will move the grasper position XR either forward to reach the food or backward. So then the animal is following the food. FSW is the experimentally applied mechanical load. And this, because this perturbation, as I said, is applied on the seaweed, so it can only be felt by the system when the grasper is closed on the food. So therefore, it's multiplying an indicator function R, which is 1 when the grasper is closed. And that is modeled here as the total activation of the protraction open, protraction closed neuron activation be larger than some threshold. And then if it's smaller than these thresholds, then it's open. So then with appropriate parameters in the swallowing mode, the system can generate heteroclinic cycle. And here I'm showing the projection of that cycle into the 3 neural muscle phase space, shown by this black trajectory. And these three walls represents the hard boundary that we call hard boundary here. These are given by these three firing rates of the neuron activation being 0, because they represent firing rate, they cannot go negative. So we have three hard boundaries, and the yellow surface represents this opening and closing boundary. That's a transversal crossing boundary. When the trajectory is below, the grasper is open. When it switches above, the grasper is closed. But together we have three hard boundaries and one transversal crossing boundary. This is a piecewise smooth system. Now we can define the test fitness. In this following behavior, test fitness can be simply defined as the averaged CVIT intake rate. So that's total amount of the CVIT consumed divided by the total time. And we want to express this using the model variables. Here I'm showing the time trace over a cycle of this grasper position. Shaded region represents the grasper is closed. And we can see that this part is protraction open and then switches to the shaded region that's protraction closed. Then after some points is doing retraction. XR is decreased, meaning that the animal is intake the CVIT, is intaking the CVIT. And here we don't have the CVIT intake explicitly shown in the model, that I didn't show in the model, but is modeled as assuming that the CVIT is moving together with the grasper when the grasper is closed on the foot and not moving at all when the grasper is open. Okay, so then with this, we can then represent these test fitness using these variables. Basically, the total amount of the CVIT consumed per cycle is the net change of the CVIT intake, or the net change of the grasper position. So that's the minus delta XR and divided by the period for one cycle. With this, we can then quantify test fitness by applying different perturbations. And here, this is the perturbation on this first neuron population. That's the sensory feedback gain term as we increase it. And here is the mechanical load as we increase the load applied on the CVIT. And for today's talk, I'll focus on this direction. We will increase the load on the CVIT and then study the robustness and also the underlying mechanism. And we can see that as we apply these perturbations, the test fitness does not change much. So that's indicating the strong, relatively strong robustness. Okay, so, and then before we study that, I'd like to give an overview of these methods. And we apply perturbation, as I said, is a small perturbation, so it's different from what Dan talked about. And therefore, to study changes in the timing, we are going to use the standard phase reduction, and Dan already introduced that method. And here, I want to mention some other limitations of this method to be able to apply to our system, is that this method is well developed for smooth systems and also has been extended to account for transversal crossing boundaries, but not necessarily the hard boundaries. And we have the hard boundary. So we extended this method further to for systems with sliding components or with hard boundaries. And also this method is very good at measuring the timing sensitivity, but only the global timing sensitivity. If we want to know how the duration of the time within a specific region changes, for example, during the closing phase changes, then we will need to use another tool that we developed, and that is called the local timing response curve. And then to check the changes in the shape, we will use the classical variational analysis. And also some limitation here is that over time, shapes of the original trajectory and the perturbed trajectory will then become increasingly out of phase. And to overcome that, we developed what we call the infinitesimal shape response curve. So later I will give a little bit more details to these methods for us to check the changes in both timing and shape, which will then help us understand how the performance changes and hence understand the mechanism underlying the robustness. Okay, so first, this iPRC. as Dan said, we can reduce our system, oscillating system, to a single phase equation, theta, and equals to this one. We here is rescale differently. So instead of the intrinsic frequency omega, here is just 1, and then plus infinitesimal shape response curve multiplying an external perturbation. So this infinitesimal shape response curve iPRC, when it is positive, that means a perturbation arriving at that phase will lead to a phase advance. If it's negative, then that will lead to a phase delay. So this curve will tell us the timing sensitivities to all kinds of perturbations. Then with this, we can then apply these to our system to understand the timing sensitivity. And this, for an asymptotically stable limit cycle, one can show that iPRC can be written as the gradient of the phase, and it satisfies the adjoint equation between switching boundaries. At the switching boundary, because F is not smooth, so dF is not defined, therefore the iPRC will experience a jump on the switching boundary. And for the transversal crossing boundary, this paper characterized how that jump can be captured by a jump matrix. For non-transversal crossing boundary, that formula no longer applies. So then in this paper, we characterized the jumps of these iPRC near the non-transversal crossing boundary. In our case, that includes the landing point when the trajectory lands on the hard boundary and then forced to slide along the hard boundary until it naturally lifts off the boundary. And interestingly, what we find is that the iPRC does not have any discontinuous jump when there is a hard landing here. It changes continuously, and moreover, the normal component of iPRC continuously decrease to 0 and remain 0 on the hard boundary. At the lift-off point, however, it experiences a non-zero instantaneous jump, and it cannot be captured in forward time, this jump. So we defined a time-reversed version of this jump matrix, which will then capture the jump from the iPRC immediately after the lift-off point to the iPRC before the lift-off point. That's by this script J, captured by this script J. So basically, that is given by this formula, which is saying that as we go backward in time, the normal component of iPRC will discontinuously jump to 0 and remain 0, and nothing discontinuous happened here. Okay, so then with this being captured, we can then apply to our system. On the top trace, I'm showing the time series of the model variables over one cycle. Top left panel shows the neural variables, and this is the muscle activation and also the grasper position. Bottom shows the iPRC corresponding to these curves over one cycle. What I want to point out here is that the iPRC is they are continuous except near these lift-off points, as I showed in the previous slide. This is where the lift-off events happen. And moreover, so this is basically telling us that perturbations on the neuron variables, they do not have a big effect on the system, on the timing of the system, unless they arrive at the right timing, shortly after the lift-off events. For this talk, because I'm considering perturbation on the grasper, so I actually only need to look at this curve. That is the iPRC corresponding to the perturbation on the XR, on the CVIT. And because the perturbation is only exists when the grasper is closed, so we only actually need to look at this portion of this yellow curve. And we can see that is below 0 is negative, meaning that perturbations to this variable will give us phase delay, so that will prolong the period. And we can integrate, let this curve times the perturbation, and then integrate that over this closing phase. That will give us the estimated value for the linear shift in the period. And we can then plot them. It agrees pretty well with the numerical result. And as shown here is saying that as we increase the applied load on the grasper or on the seaweed, the period is prolonged, is getting larger. So this is telling us the timing sensitivity to this perturbation that we considered. This is the perturbation. Next, I want to consider how the shape of the limit cycle changes in response to the perturbations. So that's shown here. We have, because we applied a sustained perturbation, so that's or you can think of that as the parametric perturbation. Now with the perturbation, we have a new limit, we have a new vector field denoted here by F epsilon, and we have a new limit cycle denoted by gamma epsilon. And this has a different shape compared with the original periodic orbit. Again, this is the perturbation that we applied. So then this gamma 1 is the linear shift in the shape. And here I'm plotting the perturbed trajectory denoted by the dashed curve and unperturbed trajectory that's denoted by the solid curve here. Again, this is the neuron variable, this is the mechanical variable. And then when we subtract them, the difference between them are shown below. And these curves are actually solutions to this variational equation. So they can be found by solving this variational equation. And here the non-homogeneous term arises from the perturbation acting directly on the vector field. Okay, so this result, if you look at this panel, it can tell us several important insights. First of all, I want to mention that this curve, that is the displacement on the grasper position, is increasing and is positive. So this is saying that this is because the grasper is getting pulled by a larger force. So it will be pulled further. Therefore, it's positive. And these positive changes will then immediately be propagated to the neural variables through the sensory feedback. XR changes on XR will be felt by the neural variables. However, we do not see, as we can see, we get a big changes in the XR, but we do not see any changes on the neural variables. And this is because of the hard boundary effect that I talked about before. Hard boundary effects are delaying the effect on of the sensory feedback. Until the lift-off point, then we see the positive bumps on this A2 neuron population. That's the retraction neuron population. And this positive displacement occurs when this neuron is deactivating. So the positive displacement here is suggesting that this neuron population is now turning off at a later time. And therefore, this neuron pool is activated for a longer time. And because of that, more retractor muscle force is built up. So we get a positive displacement here. And in contrast, we have a negative bump in this protraction open neuron population. And therefore, that leads to a decreased protraction muscle activation. So then together, the changes on these two muscle activation will then change this force generated by the two muscle activation. And what happens is that this term, which is already negative, later in the retraction cycle will then become more negative to overcome the increased load that we applied here. And here I'm showing the displacement of this term. So you can see that after the sensory feedback effect kicks in, it becomes more and more negative. One last point I want to make is that before we see the sensory feedback effect somewhere here, this is already negative. So that's suggesting the system is already doing something to overcome the increased applied load. And because we do not see any changes in the neuron variable, so that has to be due to the biomechanics and purely due to biomechanics. To understand that, we will need to look into this further. And for the interest of time, I will skip that. Okay, so this, while this is helpful in explaining some of the mechanisms here, it is still incomplete. And also I want to mention that over time, this becomes more and more inaccurate because the perturbed and unperturbed trajectory actually becoming increasingly out of phase because they have different periods. And also what I didn't mention is that this is indicating the transition from closing to opening for the perturbed system. And you can see this is also being delayed. So because they have different timing, they become increasing out of phase. Therefore, this will become not as accurate as time increases. So to overcome that, we want to introduce a method that we can actually rescale time so that we can compare them at corresponding time points. And to do that, we then introduce a rescaled perturbed time denoted by tau epsilon t. And then this new gamma 1 is what we call the infinitesimal shape response curve, which satisfy the following equation. These two terms are exactly the same as before, as the right-hand side of the variational equation, except now we have a new non-homogeneous term arising from this timing rescaling. If we want to rescale time just uniformly, assuming the system has a uniform timing sensitivity to the perturbation, then that is given by this relative shift in the period, which can be estimated from the iPRC. And then we get a uniform iSRC with uniform rescaling. However, in some cases, we may have different timing sensitivities to perturbations. For example, in the Aplysia system, the perturbations only exist during the closing phase. So it is natural to expect that perturbation has different impact on the timing sensitivity during the closing phase versus during the opening phase. So for that, we may need to use different mu1s, this term, in different regions, depending on what system we have. And that will then lead to a piecewise uniform rescaling if we rescale timing differently in different regions, and that gives us a piecewise iSRC. In different regions, we have different mu1. And to get this mu1, then iPRC no longer works because it only gives us the global timing sensitivity. So then we will need to use the local timing response curve. And this is analogous to the iPRC in the sense that it is defined as the gradient of the time remaining until exceeding this region through some exceeding boundary. And it also satisfies the same adjoint equation satisfied by the iPRC, except it has a different boundary condition. So now in different regions, we have one piece of this LTRC that can estimate different mu1. And here are the results. Now we can see the opening and closing events, they coincide because of due to the timing rescaling. And then again, if we want to focus on this yellow curve that's corresponding to the displacement of the retraction neuron activation, we see both positive bumps when this neuron is activating and deactivating. So that is again indicating that we have a longer retraction activation time. And here, because we rescaled time, so by longer, I mean longer percentage of the cycle, this neuron is activated. And that gives us a stronger retraction muscle force. Therefore, that will pull the displacement of the XR down below to be negative. Sorry about the noise. And here, when the grasper is opening again, the changes in the XR is negative, meaning perturbed XR is more retracted. That means the animal is actually swallowing more food to overcome the increased load. So that is saying the system basically compensates this load increase by prolonging the retraction phase, which allows the retractor muscle to build up more force to digest more food. Okay, and that agrees with the experimental results, which shows that the duration of the retraction muscle, retraction neuron is getting prolonged with due to the increased load, but nothing really happens for the protraction neuron. And one last thing I want to mention is that with these tools, we can also quantify robustness. Just remind you, this is the task fitness. And in this paper, the authors show that these the relative changes in the task fitness per perturbation can be decomposed into two parts. And these two parts can be exactly be estimated using the iSRC and also the iPRC. So we can estimate these two terms, and therefore we can actually use our estimated value to plot how the relative reduction of the task fitness changes over perturbation. and it agrees pretty well with the numerical results. And to interpret this better, I'm plotting the same data, except here I'm plotting epsilon over FSW. So that's representing the relative increase of mechanical load. And if we pick a point, for example, here, that is saying a 42% increase on the mechanical load leads to only about 0.5 reduction in the task fitness. So that's how we interpret this robustness. And just to show that if we use the uniform timing rescaling, then we do not get an as good approximation when we quantify robustness. So to summarize, we used this variational analysis to show that biomechanical properties actually confer resilience by immediately increasing resistance to applied load on a timescale much faster than neuron responses. And neuron sensory feedback effects on these neuron activations are largely delayed by firing rate hard boundaries. And the main effect of the sensory feedback is through shifting the timing rather than changing the magnitude. And also our analysis of using the iPRC and LTRC provides a more accurate and self-constant description of the changed shape and better understanding of the robust mechanism, and also provides a way to analytically quantify robustness. So some of the future work here that we can study robustness to other perturbations, and also using the method to apply to other limit cycles with transversal crossing boundary or hard boundaries. This is a coupled stick slip oscillator. It has hard boundary corresponding to the sticking phase. And we can use our results to actually predict synchronization of such systems. And also thank my collaborators, Peter, Hilo, and Jeff. Okay, thank you.
Thanks, Yang Yang. Questions for Yang Yang? I see Mustafa S. has a question. Go ahead.
Hi. So you showed the jump condition for this sliding solution in slide 8 or 7 somewhere. So is this just ad hoc for your system, or can we apply this for general sliding?
For general sliding
Yeah.
condition. So we're
8 or 9 or somewhere there.
Yeah, here, this one.
Yeah.
This is for any finite dimensional limit cycle system that you experience. Yeah.
Is there any relation between this jump in the iPRC, and jump in the solution of this variational equation?
In the transversal crossing, there is like a relationship, but for non-transversal crossing is a different kind of relationship, and we cannot define forward jump. We can only define the backward jump, so it's kind of different. Actually, in the variational analysis, it's totally opposite. That discontinuous jump occurs at the landing point. The normal component becomes 0, but nothing happens here.
Okay, thank you.
Thank you.
All right. And any others? Maybe I have time for one quick additional question. All right. Well, if not, thanks again, Yang Yang, for a very detailed and yeah, really nice set of mathematical analysis there. Our next speaker is Alberto Perez. Do you want to go ahead and load your slides?
Okay, can you see my screen?
Yes.
Okay.
Take it away, Alberto.
Thank you.
Go ahead.
Thank you very much for the organizers to give me the opportunity of presenting this work in this conference. I'm going to talk about phase amplitude description for stochastic oscillators, a work I have the pleasure to work with Peter Thomas and Benjamin Lindner. Well, I'm not sure if I need to motivate this talk for this audience, because we know stochastic oscillations occur throughout natural and engineered systems, and in particular in neuroscience, we have a bunch of examples of stochastic oscillations. So as a mathematician, a question will be how to characterize or how to approach these dynamics. And if I had to choose, I would like to have something, a framework which is kind of similar as the framework that we have to describe deterministic oscillations. Because we know in a system of deterministic ODEs, oscillations arise from stable limit cycles having a finite period. And as it was said before, typically these kind of systems are described in terms of a phase variable or one-dimensional variable. And during the last decade, the analysis of limit cycles through phase amplitude reduction, adding an amplitude variable, as I have been said before, provide an essentially complete understanding of oscillatory dynamics, as you can see, for example, in this review. Well, let me give you a brief detail about what is phase amplitude reduction. That is, you have a system of ODEs having a T-hyperbolic limit cycle, and then you know that it exists a nonlinear change of variables, such that the dynamics of your system express linearly, where you have the phase and you have in here the amplitude, where capital lambda is a diagonal matrix whose elements correspond to the characteristic exponents of the limit cycle, which we assume negative because we consider stable limit cycles. Computing this change of variables for large dimensional systems is something I did as a PhD in this work with my PhD advisors, Teresa and Jean Mauvet, following the work from the mathematicians from Universitat Politécnica de Catalunya, Toni Guillamont, Oriol Castejón. And well, as I was saying, the analysis of limit cycles through the phase amplitude reduction provide a complete understanding of oscillatory dynamics. And next, I aim to show how to find an analogous phase amplitude description of stochastic oscillators. To that aim, I will start reviewing this work by Peter Thomas and Benjamin Lindner, in which they define and compute an asymptotic phase for stochastic oscillators. Well, from now on, we will consider systems Langevin equations, and we will interpret it in the sense of Ito. Okay, we will consider systems with white noise. And because of adding noise, the picture changes completely. Because now we are not restricted to having underlying limit cycles. We know oscillations can arise when putting noise from a wide variety of scenarios, having what we call noise-induced oscillations, systems which oscillate because of noise. Moreover, transit times between Poincare sections are random variables. Large time asymptotic behavior no longer disambiguates initial conditions. So all in all, a shift in perspective is required to tackle this problem. Well, instead of considering individual trajectories, we will consider an example of trajectories through the conditional density. You can here the conditional density, that is the probability of being at y at time t if you were at x at time s. Okay. This conditional density evolves according to the forward and backwards equations that you have in here. Just let me say before L and L dagger correspond to the Kolmogorov forward and backwards operator. This is because using here the Kolmogorov forwards is because you are derivating respect to the forward time, and in here the Kolmogorov backwards operator you are derivating respect to the backward time. Okay, that is because that is what the origin of the name. Well, we will assume these operators L and L dagger admit a complete eigenfunction expansion. So if that happens, this eigenfunction expansion allows us to write the conditional density as a sum, where P0, suitably normalized, represents the unique stationary probability distribution. Then, under these conditions, Peter Thomas and Benjamin Lindner define a stochastic system as robustly oscillatory if these three conditions hold. That is, the non-trivial eigenvalue with least negative real part is complex. There is this relationship between the eigenvalues or the real and the imaginary parts of this eigenvalue, and all the other eigenvalues satisfy this relationship. If these conditions hold, we can extract an stochastic asymptotic phase that we will denote as C of x from the slowest decaying complex eigenfunctions of L dagger. And now let me show you an example in this paper to illustrate this. In this paper, Peter and Benjamin consider a Jean-Markov process version of the Dissecting model. So you have in here a typical neuron model in the sense that you have the voltage, the conductance variables. And then what they did is for two levels of noise, they build the L dagger operator and they diagonalize it. One level of noise corresponds to the L dots, you have in here the eigenvalues, and the other to the black. So, and they focus on the eigenfunctions associated to the eigenvalues being complex and having the least negative real part. Okay? Then this eigenfunction, which is complex, can be written in polar coordinates, so you can extract a phase from the argument of this complex number. And for example, you can see how the isochrones of this phase function compare to the deterministic ones, which are the ones in blue in this plot. It turns out that in this picture, there were one detail which was missed. As you can see, these two eyes in here were also claiming attention. Why? Because the eigenfunction associated with the least negative, non-trivial, purely real eigenvalue plays a very important role as well. In particular, it allows for the definition and computation of the stochastic isostables. In order to obtain this amplitude or isostable stochastic isostable coordinates, we maintain the same conditions as Peter and Benjamin did in his previous work, and we specialize to the case of planar systems. We will assume that the dagger has a unique real least negative eigenvalue that we will denote as lambda floquet, and we will denote its corresponding eigenfunction by capital sigma. Then, as you can check, the expected value of the amplitude function evaluated on the individual trajectories, okay, decays in the mean following these dynamics. That, as you can see, is formally analogous to the deterministic amplitude dynamics. That is why we interpret capital sigma as the generalization of the amplitude or isostable coordinate for the stochastic system, and moreover, the same way for an ODE system, the limit cycle coincides with the sets of points having zero amplitude. We propose to regard the zero level set of this amplitude function as the generalization of the limit cycles to an stochastic system. And furthermore, the same way we can take profit of this amplitude, stochastic amplitude function, because the same way for an ODE system, we were having this relationship between the phase and the amplitude and the deterministic vector field. Since we are considering for this phase amplitude construction two functions, q and sigma, whose expected values evolve deterministically, we can use it to define and compute a vector field satisfying this relationship. And as I will show you, the real part of this vector field will show us how the noise modifies effectively the underlying vector field. And what do I mean by modifying effectively? Well, it's the following. Since we are using the stochastic isostable function sigma to compute the effective vector field, you see in here, it turns out that the amplitude function of this effective vector field is exactly sigma. Therefore, while the underlying vector field of the stochastic system needs not to support a limit cycle solution, the real part of this effective vector field will have it. In particular, since the amplitude function is exactly the stochastic amplitude, the limit cycle that is having this effective vector field will correspond exactly to the stochastic limit cycle. So, as you will see in our examples, numerical examples that I next illustrate, effectively we're showing how the vector field is changed to generate that limit cycle. Well, I'm going to illustrate all this machinery by applying two different examples. First of all, I will start by an Stewart-Landau oscillator that is well known. Okay, we will set parameters so it has a limit cycle. The underlying system has a limit cycle. And first, we will start considering the case of isotropic noise. Well, what we do? We will be always doing the same thing. We build the dagger operator for this system. We diagonalize it, and we focus on the eigenfunctions associated to the eigenvalues of interest. That is, the one being complex having the smallest negative part, real part, and the one being purely real having the smallest real part. Okay, we consider its associated eigenfunctions, and as I explained before, we can use it to compute a phase and amplitude functions that we can use to compute the phase and amplitude description of individual stochastic trajectories. You can see here the individual trajectory, and in here you have the corresponding phase amplitude description. Well, what is the meaning of this stochastic limit cycle? Well, to illustrate it, let me take, instead of one trajectory, let me take a large number. I took 15 for the sake of illustration, and all of them start in the same point. And I integrate for large time. So this is what you see. And then I plot on top of that the zero isostable, this kind of candidate for a limit cycle. And you can see that it kind of captures more or less kind of a mean rotation, because there are some trajectories which complete the rotation for the outward part of the cycle, whereas there are others that complete the rotation going inwards, this curve. In other words, we can also see this because if we analyze the amplitude trajectory for an individual trajectory, we can see that it drifts around zero. By contrast, if we take the mean, if we average a large number of trajectories, we can see how they decay exponentially, regardless we are taking the logarithm, towards this curve, okay? We also studied how this curve relates to the maximas of the stationary probability distribution. You can see it in here. And we see that is near, but not corresponds to the maximas of this probability stationary distribution. Now, to continue digging into this idea of stochastic oscillators, let me consider the same model, but with anisotropic noise, okay? As always, I build the Dagger operator for this system with this noise, I diagonalize it, I focus on the eigenfunctions associated to the eigenvalues of interest, and then I have my phase function and my amplitude function, which again, I can use to compute individual phase amplitude description of stochastic trajectories. And again, if I take 15 trajectories starting from the same point and I integrate it for large time, I see how nicely the zero of this amplitude function relates with the distribution of trajectories. And again, we can see that whereas individual trajectories drift around the zero, in average, they decay towards this curve. And again, we can also discuss which is the relationship or how it relates, or to show how it relates the maximas of the probability distribution with this zero isostable. And also let me show comparing the effective vector fields for the isotropic and the anisotropic case. In black, you have the deterministic case, and in blue, you have the effective vector field for the isotropic and anisotropic case. You see in this case, there are not too many differences. Both vector fields are kind of similar, as they are kind of the limit cycles they are generating. But by contrast, in here, you can see in these areas in which the differences are larger, the effective vector field changes. Okay, I prefer to start showing this methodology by means of a system that was having an underlying limit cycle because I think it was more natural. But our setup applies to also to noise-induced oscillations. That is, as I was saying, systems which oscillate because of noise, as it is the case of the stochastic spiral sink. Okay, now we will consider a Langevin equation in this form, where this matrix writes this way. Okay, so since mu is negative, this system has an attracting focus in absence of noise. Then, following the path open in this paper by Peter Thomas and Benjamin Lindner, we can obtain analytical expressions for all the magnitudes of interest. Okay, the Dagger operator writes this way. Okay, and this matrix, okay, is the noise, the symmetric diffusion matrix that you can see here. Okay, epsilon. I remark epsilon is taking more or less like the modulus of the total noise amplitude, more or less, related with the total noise amplitude we are putting into the system. And well, we will always do the same. We have a Dagger operator, and we care about the eigenfunctions associated with the eigenvalues of interest. That is, the ones having negative real part being complex and real, purely real. And in this case, as one can show, this is the analytical expression for both functions, for the slowest decaying eigenfunction and the amplitude function, eigenfunction. Okay, so we can define a phase in this way. And since we have an expression for the amplitude, we can obtain an expression for the stochastic limit cycle. Okay, and we can also compute the effective vector field, which is quite nice expression to have, because you can see you have the original, the no-noise system, the deterministic system, plus an Stratonovic drift term, which has a real and an imaginary part. Okay, and As you can see, the real part of this effective vector field shows how the dissipative effect of dynamics, that is trajectories when being very far from the origin, they are pushed through the origin, combined with the expansive effect of noise, that is near the origin, this term repels trajectories. So it has to be something in the middle capturing that, which is exactly our zero isostable function, the effective limit cycle, sorry, the stochastic limit cycle. How can we see this? Well, because if we take this effective vector field and we express it in polar coordinates, you can see that exactly the fixed point of the radius corresponds exactly to the stochastic limit cycle, having this, the lambda Floquet, as a stable eigenvalue. So this example, as most of you know nowadays, this dynamical portrait, that is the stochastic, the stochastic spiral sink, is used intensively to describe fast brain oscillations. So we took, for example, parameters in this paper, although we could have taken parameters from a lot of works, of groups, sorry, and we computed the magnitude of interest. Okay, just to say, for the set of parameters we consider, this system has these eigenvalues, so it has a stable focus in absence of noise. And as always, we have the model, we build the Dagger operator, we diagonalize it, we focus on the eigenfunctions associated to the eigenvalues of interest, we have our phase and amplitude functions, and then we can compute the phase amplitude of individual trajectories. And again, if we want to check how the stochastic limit cycle relates with the individual with the distribution of trajectories, okay, that's what we see. We see that trajectories decaying in the mean towards this curve. And again, we see there is no clear relationship between the maximas of the stationary probability distribution and the zero stochastic limit cycle. Okay, because in this case we know it's a 2D Gaussian with a maxima in the origin. And if we compute the effective vector field, okay, you can see that near the origin it changes. In blue is the effective vector field compared to the deterministic one. Okay. And to finish, I also would like to show another example we studied, which is having noise-induced oscillations. That is an heteroclinic oscillator. We consider this system that has reflectory boundary conditions on this domain. And without noise, this system has an attractive heteroclinic limit cycle, but does not possess a finite period limit cycle. Okay, this model was studied in the paper in the previous research by Peter and Benjamin. So we studied for the same levels of noise, one weak, another larger. Okay, and again, we build the model, we diagonalize the Dagger we build the Dagger operator, we diagonalize it, and we focus on the eigenvalues as eigenfunctions associated to the eigenvalues of interest. So we can have for weak a large level for noise, phase, and amplitude functions, which also allow for description of phase amplitude trajectories. It is also nice to see how the zero isostable relates with the distribution of trajectories. You can see how it captures like a kind of a mean rotation of the system, because there are some trajectories that complete the rotation inwards, then go outwards. Well, as I was saying, no, this is nice to see by means of the amplitude because it drifts around the zero, and you see how trajectories decay in average towards this curve. And also you can see how the zero isostable relates with the probability stationary distribution, because for a smaller noise, the stationary distribution is precisely tight against the domain boundaries, because trajectories rarely visit the interior of the domain. That is why the zero isostable remains close to the domain walls. By contrast, for a large level of noise, this is trajectories spread around the phase space. Okay, that's what we obtain in this case. But the point is that since trajectories are likely to visit the interior of the domain, the zero isostable contracts, okay, towards the origin. And to finish, we can compute for the three levels of noise, for the deterministic case, for the weak, and for the large level of noise, the effective vector fields. And you can see it's very nice to see how the noise makes the effective direction of the vector field to change. Instead of being parallel in the walls, to point towards the interior of the origin, Therefore, or consequently, although the underlying vector field was not supporting a limit cycle, the effective vector field does. Let me conclude. We have shown that a phase amplitude description for stochastic oscillators can be achieved by means of the eigenfunctions of the L-dagger, the Kolmogorov backwards operator. In other words, to this work by Peter Thomas and Benjamin Lindner on the asymptotic phase of stochastic oscillators, we have put, or we have added, this work computing the isostables for stochastic oscillators that you can find on arXiv. The addition and computation of the stochastic isostable allow us to define and study two interesting ideas, which are this stochastic limit cycle and this idea of the effective vector field. Remark also that the way that we have built this phase amplitude description is analogous with the way the Koopman operator defines a deterministic phase amplitude description of dynamics, as is, for example, shown in these two very nice references. And that is not by accident, because the Kolmogorov backwards operator, L-dagger, is formally equivalent to the stochastic Koopman operator, as was, for example, shown in this reference. So therefore, we think, or we wonder about the possibility of extracting our phase amplitude functions, taking profit of these dynamical mode decomposition methods that are trying to extract these eigenfunctions from data. And just let me add very few comments about future work. Because this talk is entitled Phase Amplitude Description of Stochastic Oscillators, and it's fair to say that for stochastic systems, there are two different notions of phase. One was coined by Julius Schrevedal and Arkady Pikowski in 2013. In this paper, they define a stochastic phase that we will denote as capital theta in terms of a system of Poincaré sections possessing a mean return time property. That is, if you take a point on those sections and you integrate one mean period, the expected value lies on that section. And then we have this phase by Peter and Benjamin that is more related with how the trajectory, let's say, decay to the stationary probability distribution. So you see it's different approaches. Just let me remark that in the noiseless case, when there is no noise, these two phases coincide, as is expected, because one is like analogous to the asymptotic phase, and the other is the definition of phase that we know in deterministic systems are equivalent based on mean return times in Poincaré sections. So we ask about which are the different properties that these two functions have, those two different phase functions have. And recently, a relationship between L-dagger and this theta function was found at this work by Alexander Kao, Benjamin Lindner, and Peter Thomas. In particular, they found out that the mean return time phase satisfies this relationship. So this is the relationship between the mean return time phase and the L-dagger operator. So since this eigenfunction is also related to the L-dagger operator, we aim to explore the link between these two phases and the L-dagger operator to provide insight about the different properties of these two phases. That is a work that we have in preparation and we hope to have on arXiv during the next month. So that was it. We aim to found this kind of description, and we are very happy to show it in this meeting because we think the applications of this in neuroscience, we look forward to discuss and to study the applications of these tools in neuroscience. Thank you very much for your attention. I'm more than happy answering your questions.
Thank you, Alberto. I have a question here from Jonathan Rubin. What happens if you apply these ideas to an excitable 2-time scale system with a stable focus near an Andronov-Hopf bifurcation?
Well, I have to say it's a very interesting question. Indeed, we plan also to study this in the context of different time scales. The point is that this work is very recent, so we are really exploring it. I can tell you I have applied this to a neuron model, which has kind of two different time scales as well. And I have seen that there is kind of a curve separating, let's say, sub-threshold oscillations from spiking. So in average, let's say, you are not, I mean, you are kind of half of the time on the low threshold regime and half part of the time spiking, let's say. But that is a very interesting question that, of course, we will study in the future. I think this framework should work. I mean, at the moment, all the times I have applied it looks very robust. So, I mean, I look forward to work on that and show results in the future.
And okay, yeah, John, I guess Peter is responding to you in the chat. And then Etienne asks, what do you obtain if you apply Friedland-Wenzel theory, large deviation results?
Well, to be honest, I don't know what is that theory. I'm sorry. I don't know. Maybe Peter can ask or has a guess about. I'm sorry.
All right, yeah. So I had a question. So you mentioned that in the Stewart-Landau oscillator, your sort of mean limit cycle that you get is roughly the same as the original limit cycle.
Yes.
But that's not true in general of these systems, is it? And I guess what I was wondering is when you add noise, do the stochastic trajectories you see, do they typically shift more outside of the limit cycle? And are there any examples where if you add noise, you will get perturbed sort of stochastic trajectories that are more likely to be inside of the limit cycle?
Yeah, the key point is, let me see if I can illustrate it with this image, Zach. It's not the same to move, let's say 0x or a given magnitude in amplitude towards inside that outside, in the sense that you see this is kind of this function is kind of a Gaussian, in the sense that you see in here a change in amplitude or a change in x is very few change in amplitude, whereas in here there is very large. Okay, so my point is that is what is going on in here, in the sense that in here you are moving in amplitude, let's say more or less the same amount as in here, but then you go further because you see in here moving 0.5, let's say in amplitude in this direction is not the same as moving 0.5 in this direction because of this gradient. Indeed, this is nicely related to the amplitude, so to the gradients of the function.
Right.
So,
yeah,
yes.
I get that. I'm just wondering if you add multiplicative noise or if you have other kind of, I guess, limit cycles with less symmetry, does the mean trajectory get warped by adding noise?
Sure. I mean, I don't see any reason why that should not happen if the system is like that. I mean, in the sense, maybe as you were saying, in the case of multiplicative noise or are likely for that to happen. I mean, I don't see any reason for that not to happen.
Yeah,
I mean,
yeah.
But it's true that we consider systems that we're having like the focus in the origin, and that makes the gradient to be this way. And well, maybe that's why in most of the examples, trajectories go more to this direction than to this direction.
Right. Yeah. Okay. All right. Well, thanks, Alberto, for a nice talk and yeah, for the nice discussion there. So our last speaker today is Soajun Yu. You can go ahead and share your slides. All right, from Case Western. Go ahead, Soajun.
Thanks for the introduction and thanks for inviting me to present my work. I will talk about a homeostasis criteria for limit cycle systems, which is based on the infinitesimal shape response curves. This is a joint work with Professor Peter Thomas. And Dr. Wang just explained the infinitesimal shape response curve in her talk. And here we use it as a key tool for our homeostasis analysis. So first, what is homeostasis? Many problems in motor control involve holding a quantity to remain approximately constant despite variations of external conditions. Examples include like the stabilization of body temperature against changes in external temperature, as well as the maintenance of metabolite concentration in the face of fluctuating metabolic demands. see a species of opossum is body temperature versus environmental temperature. The body temperature changes almost linearly when the external temperature is either small or large, while in between is a broad flat region where homeostasis occurs. This general shape is called a chair, which I will mention it later. In this and many other instances, the homeostasis involves a dynamical system with trajectories that converge to a stable equilibrium point. And one looks for an interval where the equilibrium value remains roughly constant as the external parameter changes during this interval. In contrast, many physiological systems maintain homeostasis through control of large amplitude limit cycles rather than fixed points. For example, in order to maintain the lung oxygen levels in the desired range around 100, the mammalian breathing central pattern generator produces ongoing large amplitude rhythmic activity that drives the biomechanics of the airways and lungs. Other examples include like the swallowing of the Aplysia californica in Dr. Wang's talk. The rate of intake of food is to be held at constant in spite of the resistance from the food. So for limit cycle systems, the quantity of interest always change during the periods of the limit cycle, and we assume the mean value of the quantity, which is averaged around the limit cycle, is the one subject to control. So the main question is how the average of an arbitrary quantity in a limit cycle system responds to a sustained change in a parameter influencing the limit cycle dynamics. To study this question, we follow the concepts of infinitesimal homeostasis developed by Grubitsky and Stewart related to fixed point systems. And then we apply the infinitesimal shape response curve introduced by Dr. Wang to our limit cycle homeostasis analysis. Let's first back to an n-dimensional fixed point dynamical system. The last variable xn is the controlled one. Suppose at some epsilon 0, the system converges to a fixed point x0. As epsilon varies around epsilon 0, the location of the fixed point may shift as the function of epsilon, while we want the controlled variable xn to remain approximately constant. Grubitsky and Stewart formulates the notion of infinitesimal homeostasis as the condition that the derivative of the controlled variable at the steady state solution with respect to the external parameter should vanish at some point, hence approximately constant near that point. The infinitesimal homeostasis points require 0 first-order derivative. If further the second-order derivative is non-zero, then this is a point of simple homeostasis. Chill points are defined to have vanishing first-order and second-order derivatives and non-vanishing third-order derivative, like the cubic function in the example of the body temperature versus environmental temperature. So higher-order zero derivatives give more robust form of homeostasis. Such a mathematical reformulation of homeostasis allows them to use the normal form theory to discuss the universal unfoldings of the singularities associated with the homeostasis. The simple homeostasis points require no unfolding parameter, while chill points require one extra parameter. Such transformation of a homeostasis point to a normal form representation allows them to introduce the notion of a delta homeostasis region. That is the set of the external parameter lambda here, such that the output value y here remains within like plus minus delta of the homeostasis value. Here lambda is the same as epsilon in our setting. This notion of the delta homeostasis region can provide a quantitative basis for comparing the robustness of different homeostasis mechanisms. Such a method was applied to study many biological systems and all of those systems have a unique stable equilibrium for each value of the input. All right. So however, the analysis above is premised on being able to calculate the derivative of the equilibrium value with respect to the perturbation parameter. So this becomes a problem when the physiological system has a large amplitude limit cycle. Therefore, an intuitive step to study limit cycle homeostasis is to be able to calculate the change in the average of the quantity taken with respect to the limit cycle. So what do we need to calculate the change of an average? Here is an example. This figure shows a family of limit cycles generated by the Hodgkin-Huxley equations subject to a range of different driving currents. As the driving current increases from 10 to 150 PA, the period of the limit cycle decreases, and its shape changes as well. Identifying fixed point homeostasis only requires tracking the change in a scalar component of the equilibrium. But studying homeostasis in a limit cycle system requires tracking changes in both shape and timing of the orbit. So to solve this problem, we apply the infinitesimal shape response curve. But let's first look at some notations. This is a general system which has a stable limit cycle solution for each epsilon with finite period t sub epsilon. The quantity of interest is denoted by lowercase q, and the capital Q is the average of lowercase q evaluated around the limit cycle solution for one period. Then define a homeostasis criteria for the capital Q in terms of its vanishing derivative with respect to the control parameter. This is analogous to the formulation by Lubitsky and Stewart for fixed point system. Then our goal is to provide a formula for analytically calculating the derivative of Q with respect to the control parameter, so that we can using the formula to identify some homeostasis points. To calculate the derivative, the basis for our analysis is infinitesimal shape response curve. I would like to briefly remind you what it is. So it accounts for the linearized shape displacement of an oscillator upon a static perturbation. So in the linear term here, gamma 1 is called the iSRC. Here, tau sub epsilon is the perturbed time coordinate. Dr. Wang just showed that with the uniform time rescaling, the iSRC is a function of period t0 satisfying this non-homogeneous variational equation. Here we generalize this simplified iSRC equation to arbitrary rescaled time coordinates, allowing tau sub epsilon to be more flexible. So the local timing sensitivity mu1 here is no longer a constant, but depends on time t, which is given by this expression under some continuity assumptions. And it also should satisfy this condition to guarantee a a solution of T0 periodicity. And T1 here is the linearized shift in the period in response to the static perturbation, and is given by this well-known formula where Z represents the infinitesimal phase response curve. All right. So now the initial condition for this ODE of gamma 1 remains to be defined. Suppose the unperturbed periodic orbit X, the blue one, and the perturbed orbit Y are cut by a common Poincare section S at P0 and P epsilon respectively. Then we can expand P epsilon around P0 to the first order. So Py is the linear shape displacement from P0. The initial condition for the shape response curve is simply P1. Changing the Poincare section transverse to the unperturbed flow will change the direction along which P epsilon is displaced relative to P0, leading to different initial conditions and thus different shape response curves. But it can be shown that arbitrary choices of the iSRC curves are related by a fixed offset, namely the flow evaluated along the unperturbed limit cycle multiplied by a constant, which is determined by their initial conditions. So far we see that the iSRC can kind of complement the iPRC. The iPRC quantifies the effects of instantaneous perturbation on the timing of the limit cycle, while the iSRC captures the effect of a sustained or parametric perturbation on the shape of the limit cycle. The iSRC family of curves are related by a phase shift. Likewise, the asymptotic phase functions of a limit cycle oscillator are also defined only up to an arbitrary phase shift. So these are like differences and similarities between the two response curves. All right, the iSRC is closely connected to our goal of calculating the derivative of our average quantity. We begin by discretizing the perturbed orbit and the unperturbed orbit, even though they have different periods. Qx is the average of lowercase q evaluated around the trajectory of x, and similarly Qy. The difference between Qy and Qx is simply this one, and then we can approximate this term to the first order. Then we can use the shape response, the infinitesimal shape response curve to approximate this shape difference yk minus xk to the linear order epsilon times the iSRC. Taking the limit, we get a continuous formula for the derivative calculation, which is determined by the gradient of the quantity and the iSRC. Note that the iSRC is a family of curves related by a phase shift. Will different iSRC curves give different derivatives? Actually, as you would hope, different iSRC curves should give the same result for the derivative, since the sensitivity of a well-defined average should not depend on the coordinate system in which the sensitivity is measured. And in our paper, we give a proof that the phase shift associated with the iSRC cancels out when calculating the derivative. This clarifies the insignificance of the ambiguity arising naturally in the definition of the iSRC. All right, to illustrate the theory above, we considered two specific smooth systems using the simplified iSRC equation. One is the Hodgkin-Huxley model. In this application, I will mainly show some basic principles and calculations related to the iSRC. Set the driving current at 50 and apply a small static perturbation to it. First define two different Poincare sections. S1 is the one with voltage equal to 0 and increasing. See this N versus V plane. The green curve represents the S1 section. It intersects the unperturbed limit cycle at P0 and intersects the perturbed cycle at P epsilon 1. Then the linear shape displacement between the 2 points, which is also the initial condition for an iSRC, is given by this limit. Then define another Poincare section transverse to the unperturbed limit cycle at the same point P0, but transverse to the perturbed cycle at another point P epsilon 2. That is this magenta line. A second initial condition for an iSRC is given by this limit. With the different initial conditions, the solutions for the iSRC equation are different. This figure shows the 4 components of 2 iSRC solutions, illustrating how the shape changes in response to a small perturbation. The top is in the direction of the voltage variable, the bottom in the direction of the 3 gating variables. The significant difference between 2 iSRC solutions results from the different Poincare sections, but they are related by a phase shift. Black trace is the difference between 2 iSRC solutions, eta minus Kc, and the red trace is the right-hand side, phi times f, with b equal to this value. So you can see a great agreement with each other. Then to demonstrate the utility of the shape response curve for calculating the sensitivity of averages, we focus on three quantities: membrane potential, sodium current, and potassium current, as we change the value of the injected current. The black star represents the empirical average curves for the three quantities. The red trace shows the slope at I equal to 50, analytically calculated by our derivative formula, which fits very well to these empirical curves. So this shows the accuracy of the derivative formula. In this figure, eta is chosen to calculate the derivatives. If calculated by another ISSC solution could see, the differences between the derivative results are very small. So confirming that the sensitivity is independent of the measurement way of shape response. Another example is a simple biomechanical chain. Here, lambda is the input parameter, and the X network is a feed-forward excitation network. It's assumed mass action kinetics in the X components, except for the degradation of X3, which is determined by the feed-forward function eta here. Then X3 feeds into the Y network as its input. It's also assumed mass action kinetics in the Y network, except for this reaction V1 to V2, which is controlled by this feedback function zeta here. And finally, Y4 is taken as the output variable. Actually, the Y4 output exhibits small amplitude oscillations. Since the amplitude is very small, so the output can still remain near a homeostatic plateau. So the singularity was still used in the original paper by Duncan and Glubitsky. Here we adopt their model, but apply our method to show the homeostasis for limit cycles in the sense of averaging. The model has different dynamics under different parameter values of A, B, and C. And I show two cases here. The top panels are the equilibrium value of Y4, as lambda varies from 5 to 15. For small lambda, the equilibrium are stable. Then a Hopf bifurcation occurs, and the equilibrium becomes unstable and coexists with a stable limit cycle. The green curves show the maximum and minimum values of the limit cycle oscillations. And you can see the amplitude of the oscillations is very small. Then at next Hopf bifurcation point, the oscillations terminate and the equilibrium regains stability. In this second case, there are 4 Hopf bifurcation points. The middle panels show the average of Y4. In the stable equilibrium interval, the blue ones, it is simply taken as the equilibrium value. In the limit cycle interval, the red ones is evaluated along the limit cycle solution. The bottom panels show the lambda derivative of Y4 average. The solid trees, the blue and red solid trees, represents the analytical calculation given by our derivative formula. The dashed green trees is the direct numerical differentiation of the average curves from the middle panels. Again, the solid and the dashed trees shows match very well with each other, demonstrating the accuracy of the derivative formula for calculating the sensitivity of an average quantity. Note that there are some gray points which have 0 first derivative and non-zero second derivative. Recall the mathematical formulation for homeostasis. These gray points indicate simple homeostatic averages for the limit cycles. All right, to sum up, the main contribution of this work is to provide a formula for analytically calculating the first order derivative of an average quantity with respect to the input parameter. This is based on the infinitesimal shape response curve. Despite the ambiguity of the infinitesimal shape response curve, we show that the sensitivity of the average is invariant with respect to which element of the ISS family is selected. So this opens up an approach to examine homeostasis behavior of maintaining near constant average quantities around limit cycles. This first order derivative formula helps us identify the infinitesimal homeostasis points as well as the simple homeostasis points by plotting the derivative curve in the neighborhood of some points. For the chill points, a more robust form of homeostasis require the judgment of derivatives up to the third order, which complicates the analysis for limit cycle systems. So we haven't considered it yet. All right, this is my last slide, and thanks for listening. There's still some time, so I'm happy to answer all questions and comments.
Thanks, Jojun. Questions from the crowd? You can put them into chat or unmute if you prefer to just speak them. All right, I guess I'll ask one. So for all this, you assume that your system is, I guess, at least C1. Is that right? All your
under the continuity assumptions.
So is it possible to adapt any of this to piecewise linear systems, for instance, where you might still be able to have homeostasis, but it wouldn't satisfy necessarily these derivative conditions?
This is a good question. Although we haven't considered any like non-smooth examples, I think it is not a it's not a problem, because the like in Dr. Wang's talk, she developed the infinitesimal shape response curve, which is which can be used to the all of the smooth and non-smooth systems. So I think it's not a problem here to develop into the non-smooth examples.
I see. So you would just replace some of the functions in the integral with their non-smooth counterparts, but then that capital Q prime quantity would still be, you could still develop similar conditions on that capital Q prime quantity.
Yeah.
Great. All right. Any other questions for Zojun? Okay. Well, thanks again to all our speakers today. Great talk, Zojun and Alberto, Yang, and Dan. Thanks for all you for contributing to our session. I've been told to announce that we have a panel discussion, I guess, starting in I guess at 1810 Berlin time. So like in 13 minutes, there will be a panel discussion about the future of ICMNS. I mean, I think about what the plan is next year, or whether we'll wait a bit longer, or where it will be. So if you want to hear about that and contribute to that discussion, you can just go to the program and follow the link there to where that discussion is going to be. Maybe it's in channel 1. Is that right, Etienne?
Oh,
Okay.
yes. Channel 1, where we had finite talks by Olivier.
Yeah. And otherwise, I wish we were all together to have a nice, refreshing drink at one of the beautiful locations we've had as CMNS in the past, but we'll just have to save it to the next time in person. So thanks again to all the speakers and all the participants for asking questions. And thanks Etienne for getting all the tech started for the session. So Good to see everybody, and take care.
Thank you. Thank you. Bye.
Bye.
Bye-bye.